Welcome to Engineers Mindset. Now I'm going to show you how to derive a steady flow energy equation in thermodynamics. Now let's say we have a pipe at a certain height. At this point, Z1 is the inlet height, and let the outlet height of this pipe be Z2. Let the condition of pressure at this point P1, that the pressure with which the fluid enters into the pipe, and let the pressure with which the fluid exits by P2. And this is the reference line. The reference line is the point that determines the maximum height of the pipe. So this is the initial height of the pipe, and this is the final height of the pipe. Okay, let's consider an elemental portion. This is just like an elemental portion to measure the length. So let the length at the inlet be L1, and the length at the outlet be L2. Okay. Now having this, let the area of this surface, that's the inlet area, be A1, and the area of this surface, the outlet area, let be A2. When we talked about first law of thermodynamics, I said the law is simply a law of energy balance, and the law was taken considering an closed system undergoing a cyclic process, and we obtained that heat minus 4 is equal to 0. So we call this equation 1. So this is the law of energy balance, the law of the first law of thermodynamics, paying attention to a closed system undergoing a cyclic process. So we obtain that equation for it. Now what happens when the system is an open system and the initial state is not equal to the final state? So we are talking about an open system undergoing a non-cyclic process, which is a good example of what we have there. The pipe is called an open system because the inlet and the outlet are all open. Okay, and therefore the initial conditions can never be the same as the final condition. There is going to be an energy difference between the inlet and the outlet. Alright, now as fluid is flowing, the first thing I told us in the last video when I talked about the first law of thermodynamics, I said the energy that exists within the fluid is called internal energy. That is the energy that exists within a system. So that energy is called internal energy. So first of all, the energy at the inlet can never be the same as the energy at the outlet. So we'll have an internal energy at the inlet, we also have an outlet internal energy. So we can simply say, let the internal energy at the inlet be U1. Okay, let inlet internal energy. Energy U1 be U1, and outlet internal energy be U2. Sorry. Okay, outlet internal energy be U2. Therefore, the change in energy between the inlet and the outlet, change in energy or change in internal energy okay, which is simply called du, is simply U2 minus U1. Okay, so deriving the steady flow energy equation, we first of all start from the internal energy. The energy that exists within the system is called internal energy. So the internal energy at the inlet can never be the same as the internal energy at the outlet. Therefore, the change in that internal energy is also called U2 minus U1. Here U1 stands for internal energy at the inlet, U2 stands for internal energy at the outlet. So let's call this du equals U2 minus U1. Let's call this equation 2, since we already call this equation 1. Okay, so that's the first energy to determine. The very first energy is the internal energy. Also, as these water molecules are flowing through inlet and outlet of the pipe, there is bound to be what? Kinetic energy. They are moving with a certain speed, certain intensity of velocity. Okay, from the inlet to the outlet. So there is bound to be what? Kinetic energy. The energy with which they move because they exhibit a speed. And the energy of every particle that has speed is called kinetic energy. So since they move, okay, in the pipe from inlet to outlet, they exhibit kinetic energy. And kinetic energy is given as, okay, kinetic energy of flow flow AP is equal to 1 over 2 mv squared. Okay, so kinetic energy is given as 1 over 2 mv squared, where m there stands for the mass and v stands for the velocity. Now, to avoid confusion between volume and velocity, let's simply call the velocity c. Okay, so it means we can write the kinetic energy as 1 over 2 mc squared, where c stands for the velocity of flow. Okay, just to avoid confusion between volume for v and velocity for v. Okay, now notice that the internal energy is usually measured in unit mass. That's why it's called a specific property. It's usually measured in unit mass. Okay, so that's why the unit is always in kilojoules per kilogram, because it's usually measured per mass. So therefore, we also have to measure the kinetic energy with respect to the unit mass. Okay, so measuring the kinetic energy with respect to the unit mass simply means letting mass, let m be equal to 1 kg. If m is equal to 1, then it means that the kinetic energy now is now equal to 1 over 2 c squared. Okay, so let's call this equation 3. So like I said, the internal energy is a specific property. It is usually measured in units of mass. That is why the unit of kinetic energy is always in kilojoules per kilogram. Okay, so therefore, we also have to measure the energy, the kinetic energy of flow, also in unit of mass. So therefore, we consider mass to equal to 1 kg. So that means the kinetic energy of flow becomes 1 over 2 c squared, where c is the velocity of flow. Alright, so let's cancel this equation 3. Let's use the kinetic energy. Therefore, kinetic energy at the inlet is also going to be different from the kinetic energy at the outlet. So inlet kinetic energy will give us inlet kinetic energy will now be equal to 1 over 2 c1 squared, while outlet kinetic energy, okay, will give us 1 over 2 c2 squared, where c1 and c2 represent the speed of flow at the inlet and the outlet. Therefore, the change in kinetic energy becomes that the difference in kinetic energy between the inlet and the outlet will now give us change or total kinetic energy. We change in kinetic energy. Okay, change in kinetic energy will give us simply 1 over 2 c2 squared minus 1 over 2 c1 squared, and of course 1 over 2 is common, so we can factor 1 over 2 out. If we do that, we are going to simply have that the change in kinetic energy is simply equal to 1 over 2 is common, so we have c2 all squared minus c1 all squared. So let's call this equation 3. Okay, so let's call that equation 3. Alright, so 1 over 2 c squared simply means the kinetic energy per unit mass. Okay, so c1 squared stands for the inlet kinetic energy. 1 over 2 c1 squared stands for inlet kinetic energy. 1 over 2 c2 squared stands for outlet kinetic energy, where c2 stands for the outlet velocity. Okay, so the change in kinetic energy between the inlet and the outlet simply gives us the outlet kinetic energy minus inlet kinetic energy. So if you factor half, you simply need to have this particular equation correct. Okay, so the first energy you consider the internal energy. The next energy you consider the kinetic energy. Also, if you take a close look at the diagram, notice that this diagram is at a certain height. C1 and the C2. And the energy that keeps an object at a height is called potential energy. The energy that keeps an object at a particular height is called potential energy. So therefore, as this fluid flows at this point, it is at a certain height. The energy at this point becomes potential energy at the inlet. Also, at the outlet, you also have the potential energy at the outlet. And we all know that potential energy, potential energy of flow, simply P. We all know that potential energy is simply mass times gravity times height. In this case, the height is Z, so times height is simply Z. And I said that since internal energy is a specific property, it is usually measured with respect to a unit mass. We also have to convert every other energy with respect to a unit mass. And that is why we converted the kinetic energy with respect to a unit mass. So which means we also have to convert the potential energy with respect to a unit mass. And if we do that, unit mass simply means that mass is actually equal to 1. So if mass is 1, that simply implies that the potential energy of fluid is now equal to simply gravity times the height. Okay? Potential energy of fluid becomes gravity times the height. Alright, so since we know that the potential energy at the inlet will be quite different from the potential energy at the outlet, therefore we are going to have that inlet potential energy. Okay, inlet potential energy is simply the gravity is always constant, times the inlet height, so which is C1, and outlet potential energy. Outlet potential energy is going to be what gravity constant times the outlet height, so we have G(Z2). Okay, therefore change in potential energy becomes is now equal to G(Z2), potential energy at state 2 minus potential energy at state 1, G(Z1). So you have this. So that means change in potential energy is now equal to G is common, gravity is common, so you factor it out. You have G into Z2 minus Z1. So let's call this equation 4. Okay? Let's call that equation 4. Alright, so first thing first, obtain the internal energy. After the internal energy, we obtain the kinetic energy. After the kinetic energy, obtain the potential energy. After the potential energy, we will now obtain the final kind of energy that exists in the system. The final energy that exists in the system is what we call the flow energy. It's called the flow energy. Okay? Okay, so let's talk about the flow energy. We know that, recall that pressure is simply force all over area. We already know this, that pressure is simply force over area. So if we decide to make force subject of the formula, we are simply going to have that force is simply pressure times area. This is going to give us force. Okay, so that means the force at state 1 is simply pressure at state 1 times area at state 1, and the force at state 2 is simply pressure at state 2 times area at state 2. So we know that force is simply what? Pressure times area. Okay, now recall also that we said work is simply force times distance covered. So the work done is simply force times distance covered. Now the force is the force of the flow. Work done is also the work of the flow. Force is the force of the flow. Distance in this case now is the length of the pipe covered. So the force of flow is simply pressure times area, because force is simply pressure times area. Where distance is simply the length of the pipe. So the length to which the fluid covered is called the distance of flow. And in this case, the inlet length was given as L1 and the outlet length here was given as L2. So that means that the work done in this fluid now is simply equal to, in place of force, we simply have pressure times area. So we have pressure times area times, in place of distance is simply length, so times length. Okay, so that means if we now consider in terms of inlet and outlet, we can have an inlet work done. Okay, let's call it W1 is equal to the work done at the inlet. The inlet work done is simply the work done at the inlet. So that simply means at the inlet, the properties we have here is P1, A1, area of this surface is A1, and area of this surface is A2. Okay, alright, so pressure times area times length. Length at this surface is also what? L1. So inlet work done simply becomes P1 times A1 times L1. Okay, that becomes the inlet work done. Meanwhile, the outlet work done becomes outlet work done volume W2 is now equal to also the pressure as V2, which is P2, area as V2, L2 times length as V2, L2. So we have this. Right. So recall that area times length is simply volume. Area times length is simply volume. So therefore, we can simply see that initial volume V1 is the area of at inlet times length at inlet. So A1 L1 length A1. Also, V2 is equal to A2 L2. Okay, so therefore, in place of A2 L2, I can replace with V2, and in place of A1 L1, I can replace with V1. Therefore, I'm going to have an inlet work done. W1 is now equal to, this is P1 V1, and outlet work. Okay, outlet work done, W2 is simply P2 V2. Okay, so in place of A L2, we present the volume because area and volume, and area and density gives us volume. So having known this, we now obtain change in work done. Change in work done. Okay, change in work done, delta W is now equal to the final work done minus the initial work done. Final work done is P2 V2, so we have P2 V2 minus initial volume is work done is P1 V1, so we have P1 V1. Call this equation 5. Call this equation 5. Alright, so substituting equation 2, 3, 4, and 5 into equation 1 gives us what is called the steady flow energy equation. So it is called steady flow because the fluid continuously flow in and out of the system, without restriction. So the flow is steady. Therefore, the initial conditions or the initial energy and the final energy can never be the same. And this energy that takes place within the system include the flow energy or the flow work, okay, which is this. This is the work done due to the flow of the fluid as the fluid is moving. It's called the flow work. And then we'll have what is called the internal energy, the energy that exists within the system as the fluid is flowing. Okay, it's called an internal energy. We also have kinetic energy. Kinetic energy because the fluid exhibits speed as they are moving. And since they have speed as they are moving, the energy of every object that has a speed is kinetic energy. So we have the kinetic energy of flow. After obtaining the kinetic energy, since the fluid is flowing at a certain height, the energy that gives that fluid of at a certain height is called potential energy. So we also have to find the potential energy of the object. Now the sum of all these energies into equation 1 is what we call the steady flow energy equation. Now you can see from here. Okay, let's cut off this side. Alright, so recall that equation 1 was the law of energy balance, and we have that Q minus W is equal to, so this is equation 1. So I'm simply saying add equation 2, 3, 4, 5 to the right hand side of equation 1. That gives us the steady flow energy equation. So if we're adding these equations to the right hand side, we are going to have that Q minus W is equal to the first law we talked about, the first energy we talked about was that's equation 2 was the internal energy. And the internal energy gives us U2 minus U1. Okay? That was the first energy we talked about. Plus the second energy we talked about was the kinetic energy. Kinetic energy gives us 1 over 2 C2 squared minus C1 squared plus the third energy we talked about was potential energy. Potential energy was this G into C2 minus C1. So we have G into C2 minus C1. And then finally the energy we talked about was the work, the flow work, which is given as P2, V2 minus P1. Yeah, so we have plus P2, V2 minus P1. So if you leave this equation like this, equation 6 That is the steady flow energy equation. But we can also modify that equation to obtain, let's say we add up, this is Q minus W, that's equal to, now let's relate V2 to V2, P2, V2, relate U1 to P1, V1. We are going to have P2, V2 plus U2, okay, minus P1, V1 plus U1, such that if you open this bracket with the minus sign, minus P1, V1 gives us minus P1, V1, minus times plus U1 gives us minus U1. Okay, so we have plus 1 over 2 C2 squared minus C1 squared plus G C2 minus C1. Alright. Now, in thermodynamics, that is such a thing called enthalpy. Enthalpy is simply given as, we use H, that's the symbol for enthalpy. Simply H, we use H to simplify enthalpy. Enthalpy is simply the summation of flow work and internal energy. When you add up the flow work with internal energy, you obtain what is called enthalpy. So you see that P2, V2 is the flow work as the 2, where U2 is the internal energy as the 2. So that means this is actually what sum of flow work and internal energy gives us what is called enthalpy. So enthalpy is simply PV plus U. Okay. So therefore, H2 is simply P2 V2 minus U2 plus U2, where H1 is simply P1 V1 plus U1. So the sum of flow work and internal energy gives us what is called the enthalpy. So we can reform this equation or write this equation simply as Q minus W is now equal, in place of P2 V2 plus U2, we simply call it H2 minus, in place of P1 V1 plus U1, we simply call it as H1, okay, plus 1 over 2 C2 squared minus C1 squared plus G Z2 minus C1. Okay, this is 7. Alright, so equation 6 and equation 7 simplifies what is called the steady flow energy equation. So it's simply the sum of the internal energy, the sum of the enthalpy, the change in enthalpy plus the change in kinetic energy plus the change in potential energy is what actually gives us the steady flow energy equation. Alright guys, that is how you can find steady flow energy equation. In the next video, I will simply talk about the application of the steady flow energy equation in some mechanical properties, and then we'll see how far these formulas can relate to mechanical properties. Alright, thank you.